In this episode, we'll be expanding upon the first video, including introducing new concepts and finalizing the basic idea of our computer and then learning a few circuits. So in the first video, I did a very poor job of explaining binary numbers, when it basically is just every time you increment a bit, it multiplies the previous bit by 2, and that's just how the math works. And then at the end, you add all of the on bits and their specified values, where this is 1, 2, 4, and 8. You add 1 and 4, you get 5. I should have explained it better, and I apologize for that. So in the first video, we learned addition in binary, where the rule was if they were both off, you add nothing. If one was on and the other was off, the output is on. If they're both on, then the output is on, but carried. That input can carry into the next section. That's where it's supposed to carry. And if one of these are on, and this carries, this would then be on from the carry, and this would be off for the next one to be on. I didn't specify that, so I just feel like I should here. So to expand upon that, I've got a little new setup here. It's a little more interesting. But we've got an extra block over here. And what's this for? It's because subtraction works in reverse. You can't do this as normal addition. If we take our basic numbers 6 and 4, you can't subtract these with any basic logic without modifying these numbers. And here's where real tricky stuff gets into play, and where some of the circuits that we gotta make become a little fun. The B input must be the lower input, from what I understand, and it must be inverted. We have to create a circuit that will invert the B input, and all you gotta do is flip every state of the bits. So starting off subtraction, that's how we start. But we're not done. We also have to introduce a new bit. So we turn this bit on. So when introducing a new bit, it is 1 plus 1, both of which equal 1, but carried it. And so we carry it, and then we come back here. Since these are both on, we're going to carry that as well. But this is also on, which means we're going to carry this. But this is also on right here, so we're going to carry this too, because the carries act as a second addition. And since these two were both on, we automatically have one left over to put in here. And so what do we have? 1, 2, 4, 8, 16 plus 2. Now the funny thing is that since 16, the 5th bit, goes outside of our 4-bit range that we're using for this addition, we can go and pretend it's not there. It does not apply. So what we're left with is 2. And what was our initial subtraction problem? 6 minus 4. The output being 2. So that's how subtraction works. It's awfully annoying. Actually messed up with explaining it the first time around, so I'm going to have to edit it and fix that. And, yeah, that's subtraction. Hope you guys have fun learning that. So let's get into the actual layout of the computer. This is quite of a jump from just simple addition and subtraction. So what we have here is about the same setup we had over there, but just in colors. But this is grayed out. Why is that? Well, the reasoning is RAM might not always read 2 outputs at the same time. So what can we do? What we do is at the CPU, we have its own storage called cache, which will store temporary information for its modification and output. So the RAM will take data, send it to its cache, and then the ALU would work on that information in cache, and then send it back into RAM. Cache is just temporary data. It's a system register. And doing this, we could save a lot of effort of having to create a dual read RAM, which means the RAM can be smaller, and it can have more data stored in a smaller area. And that's pretty good. The user interface stays the same. The input just goes into the bus, and the output outputs to the bus. All that's nice and dandy, easy to understand. So, since we understand this, let's move on to the next part. It's the exact same thing, but smaller, and we're going to add this area. But what is this? Well, before now, we've had nothing to control what happens and when it happens. It basically just happens as we express it, but there's no actual action. The computer needs to be able to regulate what's going on, and when it's going on, and what instructions happening. Like, how is the computer going to tell the difference between whether our input is going to cache or RAM or just going to the output? Well, that's done with the program memory, and this is being representing what's called a clock. So the program memory, in this case, is going to be ROM, which is read-only memory, which is not modifiable, unlike my original computers. This data just basically sends power lines to open and close sections of the computer to allow certain things to pass through and modify in certain ways. This chunk will have a bunch of lines, say 16, 30, 24 lines, and each of those lines have an individual set of instructions, which will tell, say, the input to turn on, it to save it into a certain part of RAM, or the next one will open up part of RAM and save it into cache, or another one will say, hey, let's use cache and let's add it together. That's what the program memory does, and it connects to every part of the computer, and every time the clock ticks, it's got a cycle of a certain speed. After every time that speed cycles, it'll increment the next line of code and then execute it by sending lines to turn on and off certain parts of the computer. That's the program memory. And the clock will be attached right to it just to save space and save time. So, now that we have that as a basic understanding, I will link a video in the description which goes far into detail on the actual innards of a computer. So, we get into circuits, we see a bunch of things here that start off simple, get advanced, get simple, and then complicated again. These circuits are basically the primary circuits of a redstone computer. We need to learn these and know what they do in order to build a computer. Because all of these will be used except for that one. Because that one's just a basic version of that one. So, at the very beginning, we have two circuits, an OR gate and an AND gate. An OR gate is simply when either of the pulses are turned on, the lamp turns on. And if they're both on, the lamp is still on. There is one where if one's on and the other's on, it turns off, and that's the OR gate, Xor Gate, but we'll get there in a sec. The AND gate is different. When you turn one on, it does nothing. If the other is on, it does nothing. But if they're both on, it allows the pulse to go through. Now that's done by having two torches power an individual line in the middle, and then that line powering a torch sends a pulse. In this inverted manner, it will not output until both of these torches are off, turning off this dust and turning on this torch, having your output. That's how that works. You probably want to know how to build it. This is how you build it. It's a little too small for me to want to rebuild it for you guys. But yeah, it's basically what it is. There are different types of AND gates. We'll be using a different type of AND gate in the final build. I'll be trying to make the computer kind of tight and good looking. So we'll get there in the next video, because the next video is actually where we build the basic ALU. So this is the core of the ALU. It's called an XOR gate, or a half adder. Now, it works similar to that of the AND gate and the OR gate. That being, if one input is on, there is an output. If the other is on, there is an output. But when we turn both on, an AND gate triggers, turning off the output by turning on both of the other outputs. For example, if we turn this line on and this line is off, this will turn all of this off, powering this torch, allowing an output. Same with the other side. But if we turn both on, the AND gate turns on a torch, turning off those lines. So, what can this be used for? This allows for very specific data to be set out when using 2 bits. So for example, let's say this bit was on and this bit is off. It's like the A input and the B input. Well, it would just go through normally, because our rule is if one is on, there is an output. But if they're both on, it carries. So what do? If both are on, our new AND gate turns on, and we have a new block here, which we can tap from. Ignore that. Basically, this torch becomes our output, and that would carry on to the next bit. So, with that, this is basically how the Xor Gate works. And just to show off how to build it, let's go ahead and turn that off, or break that. We're going to have to start off with 2 blocks. We will not be using this design in the computer itself. This is just to understand how it works. Torches for the inputs, dust to affect these torches. We have dust right here. We're going to come out on these 2 blocks by 2 blocks, put torches on the end, and dust on top. Then we're going to come up here, go up. It's 1 block? No, 1 block, yeah. We're going to place a block here, and a block here, and redstone dust here. When we add this torch, it'll connect to both these lines. The last thing we can do is add a block right here, the redstone dust. That's the output of the Xor Gate. And that's basically it. It's quite simple. It does get a little fun when you try to compact it. I've had numerous attempts on doing that, but that's the Xor Gate. That's the core of the ALU. We're going to use a different circuit for the ALU, keep in mind, so don't go building anything. But using these 2 Xor gates, we can go ahead and showcase the purpose of having 2 Xor gates for an adder, which we'll get more into in the next video, of course. But if we have an output, it's 1, and the other's 0. We send it through, we have our output, it's 1. Let's just put it right here. Where the same thing happens, the output is 1. But let's say the input is 0. Output is 0 because both inputs are on. There's no output, but we still have 1 here. It cannot go here because the carry cannot go into the same digit. So it carries to the next Xor gate, which isn't here. So if we back up a step, let's pretend like an imaginary Xor gate on this side carries on to this side. Let's say these 2 are off. So now we have a carry coming in. It comes in here, and now our output is on. That's how the carry works, and that's why there are 2 Xor gates. Now that we have that basically explained poorly, let's get into memory circuits. The memory is essential toward computers and storing large amounts of information. So what we have right here is a simple repeater lock. I'll probably use this in the final build. Repeater locking is the easiest way to store information. Not the most compact, but definitely the easiest. So your input can just turn on and off. Nothing's going to be saved or go through until it is clocked. And once it's clocked, that information is stored. You can do anything with the input and it will stay the same. Your output is on. And you could go ahead and clock it again and turn it off. That's a memory circuit. Just done with a repeater, another repeater going into it, and the repeater turned on by the torch. Not the torch, the lever. And this next thing here, it gets a little more complicated and not very compact. What we're looking at is the same thing right here, but with an AND gate. That I started off with inverting the input because I can use the stored cell as the AND gate instead of inverting it later. This saves time on the reading process. So when clocking it, this is on, and when we read it, since this is on, the output is off. That's only when inverting the input. But right now, our torch is off. But when we turn the torch on, the lever on, the torch turns off. That becomes our new input. if we clock it, we still have nothing because this torch is on. This part of the AND gate. I probably should have made this like a normal AND gate. I could probably do that instead. But if we read it by turning on this line, we have our output. How do we do that? That's good to know. We do that. Why we do that is so that we're not always reading from the memory, because we want to select which one we're reading from. So we have a specific line coming in from a certain separate area, which will turn on if we want it. And that's about it, actually. That's the memory cell. Let's just go ahead and save that. And at that, we've gone into the more advanced concepts of a redstone computer. Gone into subtraction, how that works. I don't have it displayed because I was an idiot and I turned it off. We've gone into the concept of storing data at the ALU, but we can also store after the ALU, but we won't be doing that in this project. We've also talked about instruction memory and the clock, and how that increments after every cycle and goes to the next line of code in the program memory. Then we went into circuits, learned how to build an Xor gate, and we see how all of these work. Knowing all of this, we now have all the information we need to begin development of the computer. We know the parts we need, we know their basic controls and positioning, and we know how the ALU is going to function. And now we know how the RAM will store that data. So in the next episode, we'll begin working on an ALU, and that ALU will be essential toward creating a fast and useful and good starting computer. Thank you for watching my video, and be ready for the next one, because the next one gets complicated, and if you like to think as much as I do, then you're going to definitely like that video. So please like, subscribe, share it to your fellow friends, the subscribers, not subscribers, friends, whatever, you know what I'm saying. Cue uncomfortable outro and bad at talking. Now, thank you for watching. Skedaddle.